Paul is a distinguished member of the technical committee at Sandia, and he's also a former board member here of SMTA.
That's right.
Nice to see you, Paul.
Thank you, Trevor.
Now, failure analysis labs typically learn a lot of very valuable lessons when they get field returns coming back, which maybe come back 3 months later, that they can then apply to the manufacturing process. Can you tell me, what's the first approach you take to identifying defects when you get a board coming back to the lab?
Okay. First thing we do is that we isolate the board and put it aside so that we do not incur any more handling damage to it. Then the second thing we do is we ask for all the documentation on that printed wiring assembly. We ask for all the drawings as well as the field service conditions, when it went into service, its next assembly dates, all the date codes of the components or suspect components that are on that printed wiring assembly. So we gather all the paperwork. We do that immediately, primarily because it takes a while for the field service as well as the manufacturers to gain that information and be able to present it to us.
Right, okay. And I presume these boards come back in various types of different conditions as well. But you'll obviously want to know the operating environment and everything like that.
That's correct. Generally, if it's a manufacturing defect, of course, it'll come back in the most pristine condition coming off the assembly line. If it's been in the field, then it could have corrosion products, dust, dirt on them. But all of those, what we would consider contaminants, actually could be part of the story.
Right, okay. So you bring it back, you have the data, your next approach would be to isolate where the defects are, or if you know that, or what would be your next approach?
The next thing we would do is that we would look at the field failure report and begin to work with the designers to identify, to a first order, where the failure may have taken place. Which component, which via, which trace within the printed wiring assembly where it occurred. At that point, we would then take the part, the failed part, and photograph it. We'll photograph all sides of it from all angles because that provides some of the initial information that dictates what type of conditions it was in, as well as, if we get lucky, a first point failure. Right,
okay. So you have a fairly methodical, well-documented approach to this. Are there any potential liabilities attached to some of these products coming back?
Yes, there is. Oftentimes, if we find a fault that is systemic in a particular component, what we can do in the high reliability industry is we can issue a guide-up alert or a guide-up notice. Now that has a lot of ramifications because that information is then disseminated throughout the high reliability industry. The result can be a lot of feedback to that company whose product may be at fault. And as a result, one would imagine that, of course, there are legal ramifications in those types of defects.
I mean, this has always been one concern I've had about traceability. Traceability is great for reliability and these types of things, but of course the flip side of traceability is accountability. So the more that you can trace where the board came from, which machines it was manufactured on, what materials actually failed, then, as you say, the more you're opening yourself up to potential liabilities there.
That's correct, but in the high reliability industry, we look at failures the same way the airline industry looks at a plane crash. We're really not looking for placing fault on any particular component manufacturer or subassembly manufacturer. What we're interested in primarily in traceability is to be able to determine what other products in the field may be affected, what other products that are currently being manufactured may be affected in terms of them having a defect in them. So we're more concerned with getting defective product out of the field and or isolating product that's on our shelf ready to be assembled, rather than actually finding fault and looking for accountability either legally or financially.
So basically where you would stop is you would give a recommendation as to what a field recall might be. If you found a certain defect, you would say, well, this is the defect analysis we found. We know it affects 5,000 products that are out there currently in service. We recommend that they're recall for reworking.
That's correct. We would try and determine which serial numbers are attach to which next assemblies, and then pull those parts from the field that are suspect.
Right. Okay. Talking about board level defects, what are some of the typical design and fabrication causes and solutions?
By and large, in today's complex printed circuit boards, the primary target for us when we have a printed circuit board defect are vias. Vias, by and large, still remain one of the key components of a printed circuit board that are difficult to make, and as a result, they tend to be some of the more prone failure sites in our printed circuit assemblies.
You don't get enough hole fill. They don't. Chemistries leak down into them.
By and large, it's the thickness of the copper barrel.
Right.
And so that defect and the roughness of the hole itself onto which the copper is plated together become a potential site for defects, particularly in very thick boards and under harsh conditions where thermal expansion coefficient mismatches are at their best in terms of degrading the performance of that via.
Right. Now we had a short discussion just before we started the panel here about a project you worked on this summer, which was moving from LTCC to a laminate-based substrate. Tell us a little bit about that and the reasons why you would make such a change.
The reasons were technical as well as economic. The availability of substrates was becoming questionable in terms of us being able to support our production for our next systems that are coming online. In addition, we understood that there was going to be a weight benefit by going from LTCC to laminate, and so as a result, there were those financial and programmatic drivers, and then technically the reduction in weight, and the fact that we could manage the thermal management, if you will, of the RF components and the heat that they dissipated. All those factors turned us towards a full, thorough investigation of replacing ceramic substrates with laminate.
Yeah, it's strange because as microelectronics get smaller, the geometries get smaller. I would have thought that there had been a bigger requirement for LTC type substrates.
That's absolutely correct. One of the benefits in the laminate technology is that a lot of those suppliers have recognized the value of the radio frequency portion of the industry and have actually been engineering laminates to perform to levels equivalent to LTCC and other ceramic-based substrates. And so the laminate industry has been doing its job, and as a result, they have developed robust laminate technologies that can begin to look at not only 4G, but actually the upcoming 5G types of requirements for RF circuits.
Okay, interesting. Going back to the failure analysis side, what sort of contaminants do you typically find that are not associated with the EMS process that cause real issues for you?
I think by and large, what we find is that we will see environmental contaminants as water that is carrying ionics. Okay, and that's not just ionic residues from the fluxes, it's also from the environments. Of course, the harshest conditions would be those near the seaside, where there's sea salt spray that is very effective, if you will, at causing contamination. But even things such as fingerprints, as well as organic materials, paints, varnishes, can introduce some of their processing chemicals onto the circuit board that could actually cause corrosion behavior in the metal components that make up the surface features, the conductors, as well as the solder joints.
Right. Interesting. So my final question on this is going to be relating to the convection reflow side of the business. I mean, typically with large boards, what type of defects do you see, or problems do you see with the convection reflow process, with large boards with a high thermal load?
By and large, the problems we see are the coupling of warpage of the board with the coupling of warpage of large components, for example, plastic ball grid array. And so that becomes a factor in terms of convection soldering, which is probably the most controllable that we have in terms of making printed wiring assemblies.
Right.
What we're finding also is that with thicker boards, we're finding that, in fact, balancing heat between a large mix of components and that thicker board can be a challenge.
Right.
And in some cases, what we've ended up doing is putting on as many surface mount parts as we can, and then those parts that are most difficult we'll actually assemble either with selective soldering or with hand.
Really?
Yes.
Okay. That's interesting. I mean, it used to be the case years ago that when you were getting boards coming out of China, there was too much moisture in them. They weren't making them long enough. But that problem has been more or less fixed. I mean, the quality of the boards coming out of China now is considerably better.
That is a true statement. Yes, they are. And a lot of our board manufacturers are onshore and recognize the moisture problem early on. So we have to recognize it from the assembly point of view as well. That even if the boards are coming in dry, in quote, what we find out is that for the mix and the level of assemblies that we're producing, we will actually go through a bake-out process ourselves anyways, particularly for a high reliability, high valued product.
Right. Yeah. I've heard that people double baking when you get them here.
Absolutely.
Yeah.
Certainly not a process you do in high value manufacturing. Right. And so in that case, you are relying on your board supplier to have an effective drying process before they ship.
Right. Right. Excellent. Okay. Yeah. I'd imagine also assemblies that are working in high humidity environments would be a particular challenge for you as well.
Yeah, high humidity, again, when we use conformal coatings can be a challenge because conformal coatings are meant more to serve as a barrier against liquid moisture. They are still permeable to water vapor.
Yeah. And
so in that case, then we have to be concerned with how clean the board is underneath before we apply the conformal coating.
Well, it's interesting because, about 80% of the people that are applying conformal coatings don't clean.
That's correct.
Which is staggering for me. I never understood it.
Yeah.
I guess it's just a cost to cap all these contaminants under a coating.
That's correct. When we focus on the no clean fluxes, of course, they're made not to be cleaned, and the next step would be, well, we'll just conformal coat it. But there's a lot of other ancillary contamination that takes place in both the printed circuit board fabrication, as well as the printed wiring assembly that is not associated with the flux. And so when you clean a board after an assembly process, you're mitigating not just the flux residues, but also all the other contaminants, which, if they concentrate on the board, can become a factor in terms of corrosion. Right. Particularly given the fact that, again, conformal coats are not a barrier to water vapor. Right. And that eventually water vapor will pass through the conformal coating onto those contaminants.
Right. Interesting. So there you have it. A great reason why you should clean before you coat.
Absolutely.
Okay.
Yep.
Paul, it's been fascinating talking to you on this subject. I'm sure we could go on for quite a while.
We could.
It's a huge area.
It is.
But thank you for joining me today.
You're welcome, Trevor.
Thank you.
Thank you.